geopolitical climate, so that's one issue. And also it's a fairly sized market, $1.5 billion, 1 million tons of nitrogen coming to the country. What happened to all these fertilizers? They get applied to land. So mostly soil-based agriculture, 50-60% of it is lost because of the inefficiencies of nutrient uptake in soils, and then inefficiency of food processing, and then we have food waste as well. So we're left with about 20%, well actually a bit more than that, because 25% just leaves the country again as food exports, but about 15-20% of what came in ends up on our plates. And pretty much all of it ends up in our excreta, including urine. And all of these are located in cities. So here I highlighted the 3 cities that are the locations of the 3 main nodes for this ARC hub. Other way of viewing the problem of the current linear economy, so nitrogen has a big environmental footprint, particularly in terms of carbon emission. We're relying on the Haber-Bosch process based on natural gas. So that's responsible for about 2% of global greenhouse emission. So that's close to what the aviation industry is emitting. So then the nitrogen comes through, is used, and in wastewater treatment plant we invest more energy to bring it back to its original state. But missed opportunity. Phosphorus, perhaps even worse, it's mined, and it's not, you cannot really make it. So we keep mining it and mining it. What happens is that the readily recoverable resources are running out. People are talking about 100 years, after which it will become a challenge to produce food for 9 billion people on the planet. And also there's geopolitical issues with where it's located. So big problems. So because of these big problems, we look at the circular economy. You know, can we find sources where we can tap into waste to recover nitrogen and phosphorus into reusable waste? And so if we look at these balances, it doesn't look that good. You know, out of 100 that we apply onto land, perhaps 15 or so % ends up into our waste, because I already discussed that a lot of it is just leaching out through the different losses. So there's a lot more work that needs to be done in different areas, but nevertheless, it's important that we identify some starting point. So we need to work alongside the agronomists and the food industry, but from our point of view, water industry, we can try and tap into wastewater, or particularly urine, which is a fraction of it, to recover up to 10-15% of the nutrients that originally come into our country. So why urine? There's a few reasons here, so just touch on a few. 80% of the nitrogen is in the urine, but urine is only 1% of our wastewater flow, urban wastewater flow. If you look at the total market, you can only get to 10% if you like, but we could saturate the liquid fertilizer market, which is only a small fraction of the total, but it's about half of the value of the total market because of the price of liquid fertilizers, which are actually heavily used within the city boundaries. You have a reduction of carbon footprint because you're recycling nutrients instead of producing ammonia from nitrogen. So then you have reduced energy consumption for sewage treatment plants because you don't need to denitrify anymore as much. And you have also the benefit of reducing water consumption because often these urine separation systems are waterless or low flush systems. Urine contains also micronutrients and organics, which are additional benefits. We're not only getting the phosphorus and the nitrogen, but about everything else. So this is the scheme of our hub with the 4 main themes. So for a circular economy of nutrients, we need a circular hub. And this was discussed this morning at session 1, where water was the topic. For nutrients, it's the same. We can't just achieve it with technology, and that's why we have a circular hub that touches on urine collection. So we're working with toilet manufacturers. We're working with the construction industry because we need to embed these urine pipes into new buildings. We can't simply retrofit everything. Urine processing is where Sean and myself provide expertise. And then we work with the fertilizer industry, trying to generate fertilizers that are market ready and tailored for the need of the end users. End users being not only agriculture, which is hard to reach, but also like city parks, for example, where a lot of fertilizer is being used. And we foresee that this economy is mostly going to be an urban circular economy. The point source of production is the city, the consumer is the city. And these are the key CIs of the hub, including Sean up at the top, Carabir from Griffith, myself, Jeff Powell at Western Sydney University, and Jason Pryor, who's at UTS as well. So when you talk about this to people who haven't heard about unit diversion very much, the common reaction is this is never going to work. It's impossible. We need to retrofit, implement something that has never been done. But we were thinking the same thing about water recycling some time ago. So we need to be optimistic and also look at what's already been done. There's a number of locations in the world where trials have been done at building level or precinct level, particularly in Europe, but also United States. And here in Sydney, UTS is a building that is completely fitted with urine diversion. So it is possible, but it's how we scale it that is the question. So in terms of how we separate the urine, we have gone long ways from the early days where Cynthia was working on these things. There's been issues with scaling and odors, but new technologies have come on board. Here are just some of the models that have come up recently that have become really smart at trying to minimize issues such as odor and blockages. And they do work because they are in place in numerous locations. Now this slide is about the water utilities, particularly the wastewater engineers in the room. What are the benefits for a water utility? If you take nitrogen out of sewers, what do you get? Well, so this graph here shows what happens to, for example, we look at the green curve here is the volume of bioreactor to achieve COD and nitrogen removal. So if we remove about, say, 25% of the urine, we can already achieve a reduction of about 40% of that required volume. So that means if you got the infrastructure there and it's at capacity, you take 20% of the urine out and you can bring in additional population into that catchment without having to build new tanks. So I don't have time to go through all the details here, but happy to discuss during the break. Another thing that comes down is the need of recycling. If you have an A2O type process, you don't need to recycle back as much because your nitrogen load is coming down. And then you see the anoxic tank shrinking down. So there's been a lot of attempts at technologies for recovering nutrients from urine, and this is the pre-nice technologies. We got struvite precipitation. That's being developed, nitrification, distillation. This is the Swiss Airwag process. Ammonia stripping, well, they're all good, but they end up using either too many chemicals or too much energy. And so here's a very quick overview of some of the technologies we're proposing here. UGold, developed by myself together with Urban Utilities. It's a relative electrodialysis, so electrochemistry with membranes, where bacteria help to do some of the job. And we're making a liquid fertilizer as a concentrate. We achieved 90% volume reduction without using power or chemicals, with about 2.7% nitrogen, including trace elements and carbon. Next step here, scaling up, field test, risk assess, and commercialize. As part of UGold, we also looked at micropollutants. This was before NICE started. And we know that about 50% of our pharmaceuticals end up in our weed. And we found in our small trial at Luggage Point pretty much everything you can think of. And you can see some of the stuff is pretty concentrated. particularly here. Caffeine, of course, went over the charts, but also paracetamol and so on. We were able to remove, through the one-stage process, about 95% of the majority of pollutants. Then we have Sean's process, Urval. This is a combination of MBR to stabilize the urine, reduce the pH, followed by membrane distillations. 95% volume reduction and a similar composition in terms of nutrients. They also tried it on pak choi, and the pak choi grew better than the control with commercial liquid fertilizer. Then we're developing with Southeast Water a new idea of using reverse osmosis. We think reverse osmosis should not work because it's going to scale up, but we have a smart pretreatment in mind that is going to zap all the bacteria so that they're just going to die or stop growing so that they don't scale the membranes. And finally, with water array and Graphinex, we're going to try and tackle our main enemy, which is sodium. We don't want sodium in a fertilizer, and so we're going to try to use adsorbents such as zeolites, as well as low capacity deionization to tackle that. So these are our partners. There's quite a few, so you can just take a look. Maybe you'll find yourself there. Some of you would. And there's this next thinking slide that basically covered it all. There's opportunities for the water sector. You can grow cities without scaling up infrastructure. And there's new technologies that are coming on board, which will be Australian technologies. A lot of collaboration because it's a circular project, and innovation is certainly part of it. I'd like to conclude here, and thank you for your attention.